So first, I would like to thank the organizers for giving me the opportunity to present our work here. So this is joint work with Matthias Christandl, as Anna said, and he will be answering questions on the Slack channel. So feel free to ask questions there. Okay, so as you all know, maybe from watching the Shannon documentary that was shared, capacities quantify the optimal rates for information transmission over noisy channels. And in this talk, I will focus on capacities of quantum channels. And let me review some basic terminology here. So the goal is to transmit classical or quantum information over a quantum channel T. And the most general setting maybe looks like this. So you have the sender that takes classical or quantum information and encodes it into many copies of the input system of this channel T. Then it's sent to the receiver, and the receiver applies a decoding channel D, trying to retrieve this information. So what they try to do is they try to approximate in identity channel or many copies of an identity channel. This can be a classical or a quantum identity channel, depending on the setting that we are in. And okay, for every of these scenarios, I can define the coding error, which does the difference between this identity channel and the coding scheme. Can be a norm difference or other distances. And I will call this whole scheme an NM epsilon coding scheme if this coding error is epsilon. I can also optimize over END. That gives me like an optimal coding error where I have to fix like a number of identity channels that I want to approximate. And I can define achievable rates like this. So an achievable rate is a number that you can express as a limit inferior of NM over M, such that this optimal coding error goes to 0 as M goes to infinity. So this quantifies how many identity channels you can get out per noisy channel in the limit of M going to infinity. Okay, the capacities are then the suprema of these achievable rates. So we have the classical capacity C of T and the quantum capacity Q of T. And okay, most of you know that there are these capacity formulas. So we actually know in principle how to compute these quantities. So for instance, there's the classical capacity can be expressed as a regularized Holevo-Kai quantity, and the quantum capacity can be expressed as a regularized coherent information. And it's not so important for the talk what these quantities are. They're entropic quantities, but just keep in mind that there are these formulas. Now, the motivating question for my talk is a bit provocative. So it's whether these formulas, are they actually relevant in reality? And let me maybe a bit explain to you why one could doubt this. The problem is as follows. So I drew you this diagram before, and if you are maybe physicists or maybe even experimentalists, you would of course ask what these objects are really. So there's a common assumption in quantum channel theory that these quantities can be actually executed without faults. So these E and D channels, they are perfect. And of course, this is not a realistic assumption. So quantum computers are inherently noisy. And if you want to execute these channels that act on many systems, then you cannot do this perfectly. So the question now for the rest of the talk is, what are the optimal rates for sending information reliably over quantum channels using noisy quantum hardware? And to explain to you this, I need to introduce a bit of fault tolerance. And this has some overlap with the tutorial in the weekend, but I will anyway introduce these basic terms. So first of all, I need to define quantum circuits. And for this, I fixed a universal set of elementary operations. So in this talk, I will take the single qubit gates X, Y, Z, and T, the 2-qubit C0 gate, the identity gate, this is a qubit at rest, then preparations and measurements in the computational basis, and partial traces, like throwing qubits away. Then I define quantum circuits to be quantum channels that are built from these elementary operations. So something like this. So there's a circuit diagram specifying a quantum channel. Note that since I have a universal set of elementary operations, this set of quantum circuits is dense in the set of all quantum channels. So I can approximate any quantum channel as good as I want with quantum circuits. Okay, so next I need to introduce noise on quantum circuits. And for this talk, I will focus on the most simple noise model, which is IID Pauli noise. And our results work a bit more general, but, or maybe much more general, but like this is like for this talk. This Pauli noise model works like this. So elementary operations, or locations as I will call them now, fail independently with probability P. So if we have this circuit, then I throw this biased coin for each of these elementary operations, and maybe these operations fail. Now I introduce a noise channel at these failing locations. So this noise channel in this case is a uniform mixture of the three Paulis. And I do it in the following way. So for the single qubit gate or preparation, I insert M directly after the preparation, after the operation. For the CNOT gate, I insert M directly after the gate on both outputs. And for the measurements, I insert M directly before the measurement. So in this case here, I get the following quantum channel. So you see that the M might, you might have twice the M applied to at one part, which is fine. It doesn't matter. Okay, let me fix some terminology. So I denote by FP this noise model, and by gamma subscript FP the noisy circuit, which will be some quantum channel. Okay. Next, I need to review some theorem, which is the most important theorem in fault tolerance, I guess, the threshold theorem. So to protect a circuit from noise, the main idea is to implement the circuit in a quantum error correcting code. And I mean by this that we replace every of these elementary operations by a corresponding gadget that implements the corresponding operation on the error correcting code. And for the sake of this talk, this will be enough. We don't need to go more into details how this looks. Anyway, there's this, we will write gamma subscript C for the implementation of the quantum circuit gamma in the error correcting code C. And then we have this theorem that you might know. So it's a threshold theorem in the version by Aliferes, Gottesman, and Preskel, and there have been earlier versions by Aharonov and Ben-Or, for example. So there exists a family CL of quantum error correcting codes and a threshold P0, which is a number greater than zero, such that for every quantum channel, quantum circuit gamma with classical input and output, we have the following inequality. So let's go through this. So on the left-hand side, we have a trace distance between the quantum circuit implemented in the code CL, affected by the noise model FP, and it's the trace distance to the ideal circuit gamma. On the right-hand side, that's upper bounded by a constant C times this number P over P0 to the 2 to the L times the number of locations in the circuit. So now P needs to be, for this to really work, P needs to be less than P0, then this quotient will be less than 1, and you can make this right-hand side as small as you want by increasing the L. That's the issue. You can protect the circuit arbitrarily well from noise if you just increase this level L. Okay, let's apply this now to our communication scenario. So, and I want to focus on the classical capacity here. I had this picture before. So, and now as a first step, I take these quantum channels E and D and I approximate them by circuits, which I can do since the circuits are dense. Next step is to implement them in an error correcting code. But now you see that there's a slight problem here, because the channel now should receive the output of the circuit gamma E. But this output is now a logical state in this code space. So how do we get this out? How do we get the logical state into and out of the channel on the other side? And for this, so we need what I call an interface. So it's a circuit that maps between the code space and this physical space. Somehow, something like this. But keep in mind that this is a noisy quantum circuit as well. So this will add noise somehow to this whole scheme. And it actually adds a lot of noise because this here are physical qubits. So they are affected by a high noise rate. They're not protected by the code anymore. Okay, so let's formalize this. I want to, for simplicity, only consider qubit channels here. And I want to define this particular measure of how close a classical channel is to the identity. This is called the average classical communication error of the classical channel S. And it measures the average probability of S to produce a mismatch in the input, right? So this I will use to measure how close a classical channel is to the identity. Now, to define a fault-tolerant coding scheme for classical communication, I want to define an NM epsilon coding scheme. And this consists of a pair of circuits gamma E and gamma D, such that gamma E has classical input, n bits. Gamma D has classical outputs, also n bits. And we have the following long formula. So this is the average classical communication error of this whole coding scheme that I had in the image before. So first we have the circuit gamma E protected by the code C2. Then we go out of the code using the interface DEC C2 into the physical channel, then through the interface enc C1 into the code C1, and then we apply the circuit gamma D that is protected by the code C1. And in the end, we take the infimum over all the codes and these interfaces. And we want that this infimum is less than epsilon. Then we call this an NM epsilon fault-tolerant coding scheme. Now, since we have defined coding schemes, I can define fault-tolerant capacities in the same way as before as suprema of fault-tolerantly achievable rates. Note that as in the previous definition, I want this error to go to 0 in the end. So I'm not allowed to keep an error that depends on the P. The whole issue that I want, the whole difficulty of this is to get this error down to 0. Okay, and I will now show you my main result or our main result and explain to how you get there. The main result is the threshold theorem for capacity. It looks like this. For every quantum channel T and every delta greater than 0, there exists a threshold P delta T greater than 0, such that the fault-tolerant capacity of T is lower bounded by the ideal capacity minus delta, whenever the gate error probability P is less than the threshold. And in particular, we have that the limit of gate error probability going to 0 of these fault-tolerant capacities retrieves the ideal capacity. Yeah, so that's the main theorem. And now in the rest of the talk, I will sketch the proof and mention some difficulties. And for simplicity, I again will consider only qubit channels. So the first step is to choose a circuit code and interface circuits. So I had this picture before. And of course, the obvious choice for a circuit code is the codes from the threshold theorem. So, and there are actually many codes you could use, but one particular nice code family is the concatenated 7-qubit Steam code, which encodes a single qubit into 7 to the L qubits. The nice thing about this code is that you can use a product interface. So this means that every physical qubit has its own code block that is decoded by one of these interfaces. So you see here, I noted the dimension of these spaces, so it goes down to the physical level, so these interface circuits will be very noisy. So you see that maybe it's not the best idea to design these E and D operations for the channel T. Maybe what you want to do is to consider these interfaces as well. And this is exactly what we want to do. We want to develop coding schemes for this effective channel. And okay, to do so, we first have to identify the effective channel. So now I need a short intermezzo on how to analyze fault-tolerant circuits under noise. And this is again following Aliferes, Gottesman, and Preskel. So take this code, this family of codes from the threshold theorem, and every of these code spaces is of course spanned by the logical computational basis. Now, what these codes do, or what in a certain sense every code does, is that it gives you a direct sum decomposition of this whole space into summons that look like this. So it's like CL, like the code space, and there's some product Pauli operator ES applied to them. And S runs over these so-called syndromes. So we call ES the Pauli error associated with syndrome S. And maybe a bit more familiar to you, what you do is to correct errors physically, you measure the syndrome, and then you apply the corresponding ES. Note that they are self-adjoint unitary operators. So yeah, this is how these codes work. Now this direct sum decomposition gives you a very nice method of separating data and noise formally. This works like this. So this direct sum decomposition gives you a canonical basis in which you can interpret noise. And this basis is given by the computational basis transformed by these ES operators. So now I define a unitary map that goes from the whole space of 7 to the L qubits to a data part tensor a syndrome part. Particularly if I have the ES applied to a logical state, this D maps this to a data part tensor the syndrome part. And I can define quantum channel with this cross operator. This is the ideal decoder, which is called dex star. And I can define an ideal encoder, which is a quantum channel with an adjoint unitary as a cross operator. Turns out that the eng star is the inverse of the dex star. Now you should note that, so these here, they are formal operations. So they're not physical in the sense that you want to do them. They are tools to analyze quantum circuits under noise. And let me explain to you how this works. So consider, for instance, the case where I have a logical state where there's some noise on it, like some noise from this set of ES. If I apply the dex star to this, it separates the data from the noise and it maps this to the data part tensor, a matrix encoding the noise. Can even do it more complicated if I have a noise channel that has cross operators that are in the span of the ES. Then, so this says that they are correctable, this is a correctable noise. Then if I apply the dex star to this noise channel acting on the logical state, I obtain psi tensor a syndrome state where the syndrome state depends on R and in some sense characterizes R, or yeah, depending on the code, I guess. Okay, so this here, so all you should take away from this is that correctable errors transform to products under this dex star operation. And now let's use this for identifying the effective channel. So I had this picture before, and what I want to do now, so this here, this whole coding scheme under this noise model is a very complicated quantum channel. Now I want to introduce pairs of eng star and dex star formally on these lines, just like this. Remember, they are identities. Look at the encoder side or the sender side first. The output of the gamma CE circuit is with a high probability a logical state corresponding to the ideal output of the gamma E circuit, where there's some correctable noise on. So as I said before, the dex star will transform this into a tensor product. So you obtain the ideal circuit tensor, a syndrome state that in some way captures the whole noise that is on the circuit. In particular, it will depend on the circuit. On the other side, on the receiver side, you have the same thing, basically the dual picture, which you can check that how it transforms is like this. So we also get a tensor product with a partial trace. Okay, we can use the partial trace to kill some legs here, and we obtain the effective channel. Now note that the effective channel has two input wires. So it has a data input and a syndrome input. And the problem now is that the syndrome input couples it to this big state that might be entangled over different applications of these applications. And that's the issue that we have to deal with. Okay, so we have to find coding schemes, EM and DM, or these coding channels, such that the average classical communication error of this guy goes to 0. Where the sigma SM, they depend on M, they depend on the channel EM, so it's like somehow self-referential. So it's like, in general, a very difficult coding scenario. This is called a fully quantum arbitrary varying channel. So This is very difficult, but luckily we have more structure. So what we can show is that there exists interface circuits, enc-L and dec-L, such that this effective channel has the following nice convex, convex decomposition. So it decomposes into a part that has a fully quantum arbitrary varying channel NL in it, and another part that corresponds to the ideal channel T, or the channel the noise channel T that I wanted to have. This probability 2CP is a probability that the interface fails, or actually that both interfaces fail in one line. So when interfaces fail, I cannot say really anything. If they don't fail, if they work, then the channel T is recovered. And I should say that this probability of the interface failing is 2 times C times P, in particular that this doesn't depend on L. This has been shown in this paper in 2014 by Mazurek and al. Okay, so now let us construct the coding scheme in the last minutes. I want to exploit the special structure of this channel now. First step is to use a kind of Chernoff bound, which is actually precisely Chernoff bound, that lets you upper bound this effective channel for a syndrome state by an IID part, so for a channel TP tilde tensor M, plus a part that vanishes as M goes to infinity. I should know that this IID part comes with this exponentially increasing factor that we somehow have to deal with. But otherwise, we can reduce it to this IID channel. This order here is a CP order, so the right-hand side minus the left-hand side is completely positive. Good. So using some monotonicity property of this average classical communication error, I can upper bound this error by this right-hand side. So it's an average classical communication error of an IID coding scheme times this increasing factor plus some term that I can neglect. So it's epsilon M, this vanishes as M goes to infinity. That doesn't matter anymore. Now I want to find EM and DM such that the average classical communication error of this coding scheme, of this IID scheme, compensates compensates this exponentially increasing term. So it has to go to, the whole thing has to go to 0. This I can actually do using random coding. Essentially, I mean, it's essentially the same as the standard coding theorems, just that you have to make every error explicit. So it's like a bit technical to do this. You have to sacrifice a bit of the rate. So you get a function GP prime P that, you have to decrease the rate a bit that you could achieve using the normal theorems. Now, this would give you a bound in terms of TP tilde, but TP tilde is close to T. So I can use a continuity bound to relate it in the end to a quantity involving T. Still having some maybe slightly different function. So in the end, I get this lower bound on the fault-tolerant capacity, where this is this G that I had before. H2 is the binary entropy. And from this lower bound, I immediately get the corollary that I mentioned before. Let me mention one small thing here, that I cannot regularize this lower bound directly. So if I take the limit of k going to infinity, the second term will kill me. So, and this is the issue that causes this threshold here to depend on t. It's actually an open problem whether we can get rid of this. Okay, with this I want to come to the end here and advertise our paper. So we have similar results for the fault-tolerant classical capacity of classical quantum channels, where we actually don't have channel dependence here. So in some sense, this I would consider to be fully solved, or more or less fully solved, I guess. And then we have the fault-tolerant quantum capacity as well. Fault-tolerant quantum capacity, what we do there, we make a bit of a trick because you for the fault-tolerant results, you need classical input and output. So how we define this is with respect to a quantum computation. So we have a quantum computation with classical input at the sender side, a quantum computation with classical output at the receiver side. And we could define the fault-tolerant quantum capacity such that you can replace an identity channel in the middle by the coding scheme. That's a small formal trick. Yes, and with this, I want to come to the end. Check out our article, and thank you for your attention.
Okay, so thank you very much, Alexander. let me then try and find some questions from the Slack channel. So there was a first question by Zhu Kao that was asking whether the main message of this work seems to be that noisy quantum computation doesn't matter for channel capacity as long as the noise is below a threshold. And there was a lively discussion underneath, but maybe you want to also add to that.
I mean, I think it's I mean, yeah, I mean, like, so certain noise doesn't matter. I think this is what we show. I mean, but I mean, okay, actually it does matter because it decreases the capacity a bit, right? So yeah, if you want to, yeah, I mean, it doesn't matter in the sense that if the noise rate is just small enough, you can retrieve the coding rates. But this is like I guess what we always need is this IID assumption. So the IID that the failing gates are chosen IID in a sense. So if there are some correlations, I mean, then maybe it matters.
Okay, thank you. Then Richard Kueng asks, the Chernoff bound seems to give a very strong exponential decay on the second term. Correction, is this important, and could you in principle get by with a weaker tail bound as well?
Yeah, this is not important at all. So this second term here, I mean, yeah, I mean, yeah, you could have any tail bound here. I mean, this factor here is the important thing somehow. So if you could make this part a bit weaker by making and decreasing this part, this might help.
Okay, thank you. And then Frederick Dupuy is asking, how is the interface modeled exactly? It seems like in an actual implementation, the qubits inside the computers at both ends would have a completely different physical support from those that are inside the channel. At which point and how does the shift happen here?
Yes, yeah, so, okay, I don't know what he means by different support, but like, so, what actually, I mean, this concatenated codes, they are quite nice in the sense that you can consider an interface between the first level of the code, so in this case, like the 7-qubit Steam code, and a physical communication line. And I mean, there's one easy example where you just do teleportation between this. There's some error that is linear in the gate error probability P, but you can build this interface. And then you basically implement this simple coding scheme in higher and higher levels of this concatenated code. And somehow, yeah, this concatenated code, they suppress errors doubly exponentially. So by doing this like somehow L times, you get still a linear bound in the gate error probability. I hope this was more or less clear. Maybe. Yeah.
Okay, thanks. So for any clarification, there's always the round tables at the end of the session. So thank you again. And yeah, we go back to the main session. Thanks.